Hey everyone, in this video we're going to talk about section 3.4, which is about multiple angle identities. These include the double angle identities, the half angle identities, and the power reducing identities. This video is going to mainly show you the applications of these, and then in class we're going to touch on the proof side of these. So first one that we're going to discuss are the double angle identities. Okay, so these are derived from the sum and difference identities, and it comes from if alpha is equal to beta, or if u is equal to v, okay? So we get these different identities. So sine of 2u is equal to 2 sine u cosine u. Tangent of 2u is equal to 2 tangent of u over 1 minus tangent squared u. And cosine of 2u actually has three different things that it could be. Okay, and we'll have to kind of pick and choose appropriately which one we want to use in different scenarios. Okay, so the double angle identities are nice because if we have double of some sort of angle on our unit circle, using this identity gives us a nicer way to be able to evaluate that using sine, cosine, or tangent. So I don't know if I've already said this. We're going to discuss how we can derive all of these formulas in class. You're more than welcome to do this on your own at home first before you come to class. If you want to try it out, go ahead. But we're going to jump into example 1. So we're going to solve these equations in the interval 0 to 2 pi. Okay, so we are going to limit our answers. So the first one has cosine of 2x minus sine x equals 0. So this is where these identities are nice, okay? So it gives us a way to use this transformed version of cosine. We can make an identity so that way it's easier to solve for what these solutions are going to be. So cosine of 2x does have three different options: cosine squared u minus sine squared u, 1 minus 2 sine squared u, and 2 cosine u minus 1. So you can use any of those, but we have to pick and choose strategically. So because I see here that I'm subtracting a sine x, I'm probably going to want to replace this if I'm solving with something that also has sine x's in it. Okay, so that takes off the last one. And then between the first two, I'm going to pick the one that only has sine x's in it because it's going to be a lot easier to solve. Sometimes. It's a good place to start at least if it only has sines in it. Okay, so I'm going to make the substitution that cosine of 2x is equal to 1 minus 2 sine squared x minus sine x equals 0. Okay, then from there, I'm seeing that this kind of looks quadratic-like, so I'm going to rearrange it to put it into standard form. Okay, I see that my leading coefficient is negative. I'm going to go ahead and pull out or divide out a negative by dividing all of my terms by a -1. And we could factor from here, but sometimes it's just nicer to do this. All right. Okay, so what I kind of have here, and the form that this is in, is 2 times some quantity squared plus some quantity minus 1. So I think that if we were to go ahead and factor this, this would factor, let's see, to be a 2 sine x and a sine x. And then, let's see, we want a minus 1, but we want a plus sign, so plus 1, minus 1. Looks good. Okay, so now that I've factored it from here, I know that since I have the product of two factors set equal to 0, I can set each of those factors equal to 0 and solve. So I'm going to have a 2 sine x minus 1 equals 0, and a sine x plus 1 equals 0. Okay, so looking at that first one, I'm going to add over my 1. Then I'm going to divide by 2. So I'm looking for values where sine of x is equal to 1/2, okay? And we want to be in between 0 and 2 pi. So I know that sine is positive in quadrant 1 and quadrant 2, and sine of 1/2 should be pi over 6. So that would make, in this first instance, x equal to pi over 6 and 5 pi over 6. Just double checking my key. Looking good so far. Okay, our next one, I'm going to subtract over that 1, so I have a sine x equals -1. Okay, there's only one place that sine of x is equal to -1 on our unit circle within this interval, and that's at 3 pi over 2. So we do get three solutions out of this, and if I am looking at At my solutions, we do want to check to see if any of them are extraneous, but my original equation only has cosines and sines, and those are defined for all values of x. So no extraneous solutions. Okay, looking at our next one, so the next one is cosine of x plus cosine 2x equals 0. So again, it's nice to be able to make a substitution for the cosine of 2x. So going back up to the top, since my other term was just a cosine of x, let's try to choose some sort of identity that's only going to have cosines in it. And in this case, I do think it's going to be that last one. So if I make that substitution, I'm going to have cosine of x plus, let's see, that was 2 cosine squared x minus 1 equals 0. Okay, again, quadratic like, let's put it in standard form. Okay, and you'll notice that I wrote a sine squared x, so let's fix that. I promise I didn't mean to do that. Okay, taking a look at this, I see that it's in the same form as the quadratic above, just in this case we have cosines, the one before had sines, so it's going to factor the same way. So I'll have 2 cosine of x minus 1 times cosine of x plus 1 equals 0. So again, we have the product of two factors set equal to 0. I'm going to set each of those factors equal to 0. So 2 cosine x minus 1 equals 0, and cosine of x plus 1 equals 0. So for this first case, adding my 1 over and dividing by 2 is going to give me that cosine of x is equal to 1/2. Okay, and so cosine of x is going to be positive in quadrant 1 and quadrant 4. And it looks like this is the case when x is equal to pi over 3. So in those quadrants, it's going to be pi over 3 and 5 pi over 3. Okay, for my second one, I have cosine of x is equal to -1. There's only one place that cosine of x is equal to -1 within this interval, and that's at pi. Okay, again, checking extraneous solutions. I think we're in the clear though, because both of these terms before were cosines, which is always defined for all values. So we're good there. Okay, we're going to flip over our page, and you'll notice that the next page, example 2, we're going to have a series of different trig identities that we're going to use. We're going to wait, and we're going to do these in class. So we are not going to do these in the video. This is going to give us kind of a talking point in class, so we can save those, and then we're going to skip over our page. One more. Okay, so we've talked about the double angle identities. We also have our half angle identities, okay? And so these are really useful to be able to evaluate angles that are not on the unit circle, okay? So just like we had the sum and the difference identities kind of gave us a way to use unit circle values to evaluate, you know, trig functions at non-unit circle values. Same thing goes with the half angle identities. So in this case, our forms are going to be sine of u over 2 is equal to plus or minus the square root of 1 minus cosine u over 2. Okay, cosine is going to be equal to plus or minus the square root of 1 plus cosine of u over 2. And then tangent has two forms. It's equal to plus or minus the square root of 1 minus cosine u over 1 plus cosine of u, which actually does simplify out to be 1 minus cosine of u over sine u. We are going to talk about why this is in class, but if you want to kind of explore like why those two are equivalent on your own, you're more than welcome to, but we'll talk about that in class, okay? So the half angle identities, like I said, really helpful to be able to evaluate things that are not on our unit circle. So for instance, the first example we're looking at is cosine of 195 degrees. Okay, so if I think about where 195 degrees is on my unit circle, that was not a great circle. Okay, well, I know that 180 would be here, so 195 is going to be just 15 degrees more than 180, okay? And in that case, that doesn't fall on any of our unit circle values. So this is where our half angle identity might come into play. Okay, so what we're going to do is, since this is equal to 195, we're going to figure out what value I need to divide by 2 that's going to give me 195. That's going to be our value of u that we're going to end up using later on. And the goal to be able to use a half angle identity is that value of u does need to be a unit circle value. Okay, if it isn't, then we're out of luck and we might have to think about something else, or we can't use an identity to evaluate it, okay? But since this is an example in the notes, it is going to work. So let's think about what that would be. Okay, so 195 times 2 is going to be 390. So I'm looking at cosine of 390 over 2. So the value of u that we're gonna use is going to be 390. Okay, and so just thinking about where 390 is, so on my circle, I know that 360 is here, that's 2 pi, so 390 would be 30 more, okay? And so if this is a 30-degree difference, that means that 390 is coterminal with 30 degrees. Okay, and we know that 30 degrees is equal to pi over 6. So we're in the clear. Things are looking good. Okay, so for this, we're going to evaluate our identity with our value of u. Now, we did say that 390 was coterminal with 30, or it's coterminal with pi over 6. So any of those are going to work to plug in. I'll start with the 390, though. So this is going to be equal to plus or minus the square root of 1 minus cosine of 390 over 2. Okay, now we said that 390 was coterminal with 30, so this is equal to plus or minus the square root of 1 minus cosine of 30 over 2. Okay, so since that's a value on our unit circle, we are able to evaluate with it. So that's equal to plus or minus the square root of 1 minus cosine of 30 is square root of 3 over 2. All right, we're going to manipulate that in a second, especially because we have this fraction and a fraction ordeal, and we do want to manipulate that. But we do have a plus or minus thing that we need to take care of here, okay? So it's not the fact that there's two values, there's not a positive, not a negative, it's either one or the other. So what we need to do is we need to figure out which one would be which. And the way that we're going to do that is we're going to look at the placement of where this original angle was. Okay, the original angle that we were trying to evaluate was cosine of 195, which we said was right here in quadrant 3. Okay, so what do we know about the signs of cosine in that quadrant? Well, if cosines are our x values, we do have negative x values in this quadrant, so I do know that this value needs to be a negative because we're in the negative x's. So what that means is that we want to choose the negative here. Okay, so something that can be a little bit confusing that I just want you to really focus in on when you're going through these problems. We did have a 390, which was in quadrant 1, which was great, but that wasn't the original problem. The original problem was trying to figure out what 195 was. So you go back to the original to figure out what your sign needs to be based off of the quadrant that it ended up in, okay? All right, hopefully that's squared away. Let's get to solving this and simplifying a little bit more. So, we do have a square root and a square root. It is going to stay like that, so don't freak out, but I don't like the fraction in a fraction. So, negative. And I might split this up along our common denominator at least to start. So I'm going to have 1/2 minus, and then the square root of 3 over 2 will be the square root of 3 over 4. Okay, if you wanted to, you could leave it just like this. That's totally fine. I do want you to be aware of how you can manipulate it, just in case this is a multiple choice question, like how you get your answer to maybe match other things. Okay, we're going to get a common denominator to do that. So my common denominator is going to be 4. So I'm going to scale up that first one by 2. So this will be equal to negative square root. This will be 2 minus the square root of 3 over 4. And that will be our final answer. Okay, sweet. We're going to look at one more. Okay, so we're going to look at tangent of 7 pi over 8. Okay, so you'll notice that that first one was in degrees, the second one is in radians, but we're still going to use our half angle identities to do that, because I know that that pi over 8's multiples are not our unit circle values, but pi over 4's are. Okay, so I'm going to rewrite this to be tangent of 7 pi over 4 over 2. Okay, so the value that we are using as our reference angle is going to be 7 pi over 4. Okay, first though, let's try to figure out where on our unit circle our original angle is. Okay, so we're at 7 pi over 8. I know that if we had 8 pi over 8, that would be equal to pi. Okay, and so pi is here. So 7 pi over 8 is going to put me into quadrant 2. We're going to be down here. So that'll be important, again, when we're looking maybe at signs of some things later on. But that's the angle that we're looking at. Okay, so since this is a tangent problem, I do see that there are two possibilities that we can use. Okay, let's use the first one. Okay, and the only reason I want to use the first one is I want to have a class discussion, again, like I said, about why that second one is equivalent. Okay, so we're going to use the plus or minus square root of 1 minus cosine of u over 1 plus cosine of u. And I need to write that down. All right, so this will be equal to plus or minus the square root of 1 minus cosine 7 pi over 4 over 1 plus cosine of 7 pi over 4. Okay, so 7 pi over 4 is going to land us over here in quadrant 4. Okay, I know that since this is quadrant 4, our cosine values are going to be positive, and then 7 pi over 4 is coterminal with pi over 4. So this will be equal to plus or minus the square root of 1 minus positive square root of 2 over 2 over 1 plus the square root of 2 over 2. Okay. For the signs, before we fix what this looks like, let's see. So going back to what we choose, tangent of 7 pi over 4 is the original angle, so I am looking here, okay? So I know that tangent is equal to like our y values over our x values. So in this quadrant, we have positive y values and we have negative x values. So the overall value of tangent is going to be negative, okay? So with that being said, we have negative. Okay, and then let's try to fix our signs here. So we could try to break this up into, again, the common denominator that we have. The only issue that we might have with that is the fact that we have, sorry, I'm like coughing a lot. We have two things within the denominator, okay? So before we had just one denominator of 2, that was kind of nice. I think maybe our best bet here is let's rewrite the numerator and denominator to have a single numerator and denominator, and then we can multiply by the reciprocal. So if I did that within the numerator, I need to make this bigger, big square root. Okay, this is going to be 2 minus the square root of 2 over 2. Okay, by turning the 1 into a 2 over 2. And then same thing with the numerator. This is going to be over 2 plus the square root of 2 over 2. Okay, within this, if I multiply by the reciprocal of the denominator, I'm going to have 2 minus the square root of 2 over 2 times 2 over 2 plus the square root of 2. Okay, and I see that my 2's will cancel, and then this will be equal to negative square root of 2 minus the square root of 2 over 2 plus the square root of 2. Okay, and I think that's actually honestly as far as we can go. I do have a big square root over this, but really there's not a whole lot more that I could do here, that I at least want to do. Or, do we explore this in the video? we'll leave it like that for now. And then again, when we get to class, remind me, let's talk about how we can maybe manipulate this a little bit more, because we know that it is equal to something else. So I do want to prove like why those two are equivalent, but I'm okay if we just leave this here because I don't want this video to be too long. Okay, the last one that we have are the power reducing identities, okay? And I'm gonna be honest, we don't do a ton with them, but they are handy in a pinch, and they can also be helpful to us when we get to calculus, okay? So the power reducing identities purposes is that we know that sine squared x can be rewritten so there are no exponents or powers into it. So like we have 1 minus cosine of 2x over 2. Cosine squared x is 1 plus cosine of 2x over 2. And tangent squared x is equal to 1 minus cosine of 2x over 1 plus cosine of 2x. So again, you'll notice that there are no examples with this. Their main purposes, and their main, at least the help that I've seen from them, is it's really nice to be able to integrate in calculus with them, because it provides us with another opportunity to integrate. We're not out calculus right now, so there's not a ton of examples that I want to do with them, but in class we are going to prove why these relationships exist. So no examples, but I do want you to see why they're equivalent. So we're going to pause the video here. We'll finish up the rest of the examples, and we'll definitely talk more about this example and how we can manipulate it to match the other one eventually. So that's all for this video, and I will see you all later.